So today is the review lecture of Challenger Mishra. This will be the first lecture on a series of 3 lectures on learning to work with learning machines. That's what the first lecture is.
Hi everyone, I'm Challenger. Thanks for coming to this talk, and thanks for the wonderful title, Learning to Work with Learning Machines. I had nothing to do with it, but I was jealous. So what I wanted to talk about today is something that I've been exploring with a couple of my friends. One of them is here, Shubhayan, and the other is sitting in sunny California, finishing his PhD. So I wanted to talk about conjecture generation and its importance in mathematics, and how to actually generate interesting conjectures using machine learning. And to begin, I wanted to tell you a short story. Apologies to those who have heard this story a couple of times, so bear with me. So in the year 1900, David Hilbert proposed a list of 23 challenges. And the purpose of posing these 23 problems was to indeed drive development of mathematics in mathematicians' attempt to resolving such challenges. And in particular, one conjecture that Hilbert proposed is particularly interesting to me, because it sort of exemplifies the role of a good conjecture in driving mathematics, not only in driving not only different kinds of mathematics, but in also having impact in associated fields such as machine learning. So the 13th problem is quite easy to state, much like many of Hilbert's other problems. And the 13th problem states that given a degree 7 polynomial equation, which can always be reduced to the form that you see on the screen, can one write down the solution as a composition of a finite number of 2 variables? So this was the question that Hilbert posed in the year 1900 at the ICM in Paris. Now, fast forward 50 years, and Soviet mathematicians Kolmogorov and Arnold had a look at this problem, and they realized that it's a tough one. And they attempted to resolve it for one particular case of the original problem, which is to do with the continuous case as opposed to the analytic case. So Kolmogorov shows in the year 1956 that it is indeed possible to construct any to write down the solution as a composition of composition of 2 variable functions, and Arno joins in the effort, and they have a mathematical wager of sorts. So Arno, who was the supervisee and only aged 19 at that time, sort of bet against the conjecture, and Kolmogorov bet for the conjecture, and together they wrote a series of papers, and those papers ultimately showed that indeed it is Hilbert's 13th problem has a solution in the affirmative for continuous functions, but they did one better. So they came up with a very interesting representation theorem that showed that actually only one variable. Well, Arnold was only 19 years old at that time. It puts a lot of us to shame. Yes. It's a mystery to me. I mean, a lot of the questions Hilbert posed were motivated by the fact that they might drive developments in mathematics, or the problems themselves might be useful for mathematics itself. But it's not known to me why this particular form was great.
And this equation is 0.
I believe you. All right. So what is this representation theorem? So the representation theorem goes by the name Kolmogorov-Arnold representation. And it was a mathematical supernova for various reasons. So if you look at the form of the representation theorem, which let me describe quickly. So on the left-hand side is a continuous real valued function of many variables, which is f. And on the right-hand side, as Hilbert demanded, is a compositional structure. But if you look carefully at the form on the right-hand side, you'll see that it's a function. The argument that appears in the interior function consists of only one variable. So what this representation theorem is saying is the only true multivariate function in the real domain is the sum function, which is quite absurd to think of a priori. Now, there have been several refinements of this representation, and there are many variants of this representation. But the important thing to note here is that it's an exact representation of the function. Now, why do we care about this? So, some of the interpretation of one of the interpretations of some of the functions that appear in this representation is that of a space-filling curve. Meaning, you think of some of the functions here as generators of curves that fill out a compact space completely. And this presented a new view of geometry, which is different from a smooth notion of geometry that mathematicians were used to up until that point. So, as such, this was a mathematical supernova, and Heck Nielsen, who is a machine learner, describes this result as describes the story behind this theorem, and says that the Kolmogorov theorem was discovered during a friendly mathematical duel between Kolmogorov and fellow Soviet mathematician Arnold, and Kolmogorov won, settling the bet. So why do we care about this in the modern day? So if you fast forwarded 3 more decades and you reach the 1980s, Heck Nielsen came across this result, and he quickly realized that, wait a minute, the form of this representation, being compositional, is indicative of a neural architecture that can represent this function exactly. Now, this was in the 80s, and in the 80s, there was the appearance of the universal approximation theorems, which lots of you might be familiar with. The universal approximation theorem guarantees the ability of a neural architecture to approximate, some function or some process you are trying to model. But as a theoretical physicist, it's always a little unsatisfactory because it's an approximation. However, if you look at this kind of a functional representation or the neural network that Heck Nielsen built out of this representation, that is exact. Question. So Heck Nielsen builds these networks. It's a 2-layer neural network that can exactly represent a multivariable real value function. And he builds these networks, calls them Kolmogorov mapping networks. Now, if you put this result in the context of modern deep learning, you realize the following. So in modern deep learning, we typically have very large architectures which help you model very many interesting functions, and there are applications in real world problems and otherwise. So in a sense, this theorem or this representation shows why deep learning actually works. So these two-layer neural networks that Nielsen built, these Kolmogorov mapping networks, although they are exact, the nature of some of the functions that appear inside this and their interpretation of the generators of space-filling curves means that these functions behave quite wildly. So in order to represent a function, you have to, on the left-hand side, you have to find a description of these generators of space-filling curves and other associated functions. The reason deep learning works is you start controlling the wildly varying behavior of these inner functions by adding more layers. So the Faustian offer you make is in terms of the approximation, but the advantage then becomes that you are able to deal with the computational problem, the underlying computational problem that we typically solve in machine learning in much more easily. In some sense, you can think of a machine learning pipeline as a twofold thing. You can think of machine learning providing you with interesting architectures that rely on tons of different parameters, a very large number of parameters, and you are ultimately solving an optimization problem, which is typically very hard to solve. Yes. So this conjecture, therefore, sort of zooming out a little bit, the conjecture that Hilbert posed in the year 1900 gave us a new interpretation of it, but it also had a deep impact in establishing that neurocomputing is on solid mathematical footing, and it provides an explanation of why modern deep learning actually works. Question. I have not come across it. People have attempted to generalize this representation to complex functions, and although it's not clear that it cannot be done for certain classes of complex functions, but there are certainly counterexamples. So there are complex functions which cannot be accommodated in a representation of this form. So this is an example of a good mathematical conjecture. So it drove development in a few different areas of mathematics, and it had a deep impact in modern machine learning. So Hilbert's conjectures beg the question, what constitutes a good conjecture? And a priori, I'll tell you that this is an incredibly hard problem, and there are several folks who have thought deeply about this for a number of decades. There's Mike Douglas. So we acknowledge the hardness of this question, and show. From here on, I'll talk a little bit about our approach to generating interesting conjectures like this. But before that, I'd quickly like to mention that one of our students in the computer laboratory, Theo, he originally started working on exploiting these representations in a machine learning context, but quickly the thesis evolved into something else, and with a lot of help from Oisin and Justin, he wrote a beautiful thesis on geometric sampling techniques. So if anyone is interested in exploring these interesting representations, which pretty much no one works on in the machine learning domain, then please have a chat after. So I want to point out this wonderful article in Quanta that string theorist Robert Digraph wrote. And the article is titled "The Subtle Art of Making Conjectures." And Robert Digraph points out that there can be many different types of conjectures in mathematics, and a lot of them might be trivial, but there are some commonalities for good conjectures. So he lays down a bunch of criteria which I have distilled here. And they are as follows: that a good conjecture must be non-trivial. we can all agree. 1 greater than 0 is not a good conjecture. It's true, but it's not very useful in understanding mathematics further. There must be substantial evidence in favor of the conjecture. So there are a vast number of problems that appear in mathematics, which are incredibly easy to state, and they appear in volumes in the context of number theory, for instance, which is partly what brings all of us together here. So, for instance, Goldbach's conjecture or Collard's conjecture, they are examples of problems which are not only easy to state, but there is a substantial evidence in favor of it. There are other conjectures which makes one does not take lightly, and such as the Riemann hypothesis. And the zeros of the Riemann hypothesis, the first gazillion zeros ordered by height, have been checked, and they lie on the line they're supposed to lie in. So there is an incredible amount of evidence in favor of some of the still unresolved conjectures that are a matter of active research in lots of different areas of mathematics. Now, one aspect of conjectures like the Riemann hypothesis is that mathematicians have been able to form entire mathematical universes around them. There are loads and loads of equivalent formulations of Riemann hypothesis. A lot of interesting theorems are contingent on the Riemann hypothesis, and effectively they can unlock new mathematics themselves. Presumably, Robert Digraph has an interesting quote from John Conway in this article, who says that a good conjecture must be outrageous. This is a true Conway style of doing mathematics, and it is indeed true that often some of the most important results in mathematics when they appear, they seem to connect completely disjointed fields of mathematics, and it is in that sense that Conway would have presumably said that good conjectures must be outrageous. Now, Robert Digraph has a sort of warning for folks trying to make conjectures in mathematics, and says that if a conjecture is proved within a few months, then perhaps its creator should have wanted a bit longer before announcing it to the world. And we will absolutely ignore this sagely advice for the following reason. And the reason is that a lot of interesting conjectures have been posed by many famous mathematicians over the last decades or century. But we are sort of in an era where it is possible, or it seems like a promising approach to finding or discovering new mathematics using this beast of a tool that is machine learning. So the purpose of this talk is to show that it is possible to make conjectures in different kinds of mathematics, and it's important in that pipeline to talk to domain experts and computer scientists and machine learners and develop a principled approach to finding conjectures instead of wanting to get lucky or making accidental discoveries. Right. So let's consider a class of conjectures. So the class of conjectures we have been working on are inequalities. I don't exactly remember why I chose to work on this, but I remember being in Berkeley, visiting Shubayan, who is one of the co-authors of our paper, and working on this, and he did not object. So that's the only reason. But some of the practical reasons are that inequalities appear everywhere in mathematics. They're ubiquitous, and there's wide-ranging applications. You can think of versions of Riemann hypothesis which can be written down in the form of an inequality, the subadditivity of the prime counting function known as Hardy-Leavenworth conjecture, they are all in the form of inequalities. And if you are an applied mathematician and you care about some specific application, then it's also useful in bounding interesting quantities of important quantities of interest. Shubham pointed out this book written by Hardy, Littlewood, and Collier almost 100 years ago, called Inequalities, and it's a fantastic resource for identifying inequalities that are known or conjectured across a vast range of different mathematical disciplines. And we sort of considered, why inequalities was considered by great mathematicians. And it seemed like there wasn't a unifying reason. Their reasons were more practical, that mathematicians who end up discovering new things might end up rediscovering old things, and there should be a good resource for that sort of brings together all the results of this form. And so they ended up writing this book, and it's a very interesting resource for inequality type results, theorems, and conjectures. So our goal in this work is to build an oracle that interacts with mathematicians with the sole purpose of generating good conjectures in the area of expertise of the domain expertise. And in our pipeline, we will ensure that the conjecture satisfies some of digraph's criteria, such as terseness or evidence or vast amount of evidence in favor of these conjectures. And a lot of the other criteria that digraph and others thinking about this kind of questions are hard to formalize because they are currently subjective. It's difficult to exactly define the amount of outrageousness a conjecture might possess. So one of the things we realized during the course of this project is to ask ourselves the following question: that is there an organizational principle for these conjectures? So we pose the question: is there any structure in this space of relations of the form F less than G? And the motivation behind looking for structure in the space is really a physicist's approach to formulating theories. As we know, in modern theoretical physics, theories are built around symmetries and their invariants. Once you have information about invariance of a physical system, you can go quite far. For instance, Newton's second law is equivalent to translation symmetry. Einstein's relativity is equivalent to invariance under diffeomorphisms. The standard model of particle physics is invariant under gauge symmetries, and so on and so forth. So we ask this question: is there any structure in this space of relations? So enter my personal hero, Emil Noether, who did groundbreaking work on classical invariant theory more than 100 years ago, and has had a tremendous impact in developing modern theory. And thanks to her, I could finish a couple of chapters in my thesis, thanks to the technology to develop. So symmetries are indeed a guiding principle for theoretical physics, and we wonder if it can be a guiding principle in generating conjectures of this form. So let's start getting a little more concrete. So let's define a couple of different spaces. So very broadly speaking, we have two spaces. One we call the space of relations, and the other we call the space of conjecture. Space of relations are mathematical statements of the inequality form that may or may not be true. In fact, they might even be false. So, things like 1 less than 0 will be a point on this space of relations. Within this space, we define a second space, which we call a space of conjectures. Now, this space consists of points f comma g being continuous functions, such that they are true on some amount of data that you might have access to. So, for example, we heard a lot of interesting talks on elliptic curves and murmurations and so on and so forth. And a lot of data has been collected in this LMFDB database based around that. And so the conjecture space is a function of some compact subset of Rn as well, meaning that as you increase the domain of validity of the conjecture, you approach a theorem. Although that's not an approach we are considering, but it's helpful to. Questions so far? Yes.
So these conjectures, they're true over D, and you're hoping they're true over some larger domain.
Exactly. Yeah.
But you don't expect it to.
Yeah.
Like,
That's right. Yeah. That's why we call it conjecture and not theorems.
But if I give you, let's say, 1 minus x and 1,
Yeah.
this is true for x less than 1. Yeah. And if 1 is 0, let's say.
Some domain, yes.
So then you would ask, like, for which domain is it true?
That's a very interesting question, actually. So far, our approach has been yeah, but that's over. Thanks. To answer your question, we consider functions of the form f, the inequalities of the form f less than g, likely, where f and g are functions defined over some subset Rn. Omega is so interestingly, it's very interesting you mentioned this because when we initially did this work, we realized that we have paid no attention to the domain of validity. Although, as you point out, there might be interesting inequalities of this form, inequalities rather, which might be true on some useful domain, but not otherwise true. And there might be a way of characterizing all of those things in the following fashion, and that relates to something called O-minimality in model theory, where if you the domain of validity, domain of the function to be something called a definable set, then that might help us characterize inequalities as a function as well. So these are some conversations I'm having with Philip Candelas and Jonathan Pila in Oxford, but we have made absolutely no progress. But it is certainly within in our interest to consider the role of the domain in this situation.
These functions, these are just any functions which are just bounded of D, or you want them to be bounded?
So we take this, we take f and g to be continuous functions defined. That's the only condition we place on. Yeah, it will be. Yeah. So nonetheless, let's proceed. So if you note that the point 0, 0 does not satisfy 0 less than 0 or 0 greater than 0. So it cannot be in the conjecture space, it's rather in the space of relations. These things don't have the structure of a vector space. And in fact, we have kept all sorts of generality up until now, but it is possible to impose a lot of structure on the conjecture space by specializing this class of functions. We might choose to work over polynomial rings or other useful situations. So, but in what follows, we are still quite general. So we ask the following questions. We ask, what is the largest group that acts linearly on C? Now, yes. Yes, it won't. That is correct. That is correct. However, there is a point about this. I'll make in a couple of slides. Yeah.
There's a reason you only consider strict inequality, but at less than equal to G is the reason why you don't consider less than or equal to.
So the strictness seems to be important in some of our proofs about how the statements we are making here. But since you asked, actually, considering equality is also within the purview of what we are developing here, because if you think of the following very rather trivial statement, that if f is not less than g and f is not greater than g, then the only logical conclusion is f is equal to 0. So from a practical point of view, in our machine learning enterprise down the line, we can also we are also able to look for conjectures of this type. All right. Okay. So we pose these group theoretical questions because we have put on the physicist hat at this point. So what is the largest group acting linearly on C? And are there any free group actions on this space? Why do we want free group actions? Because if we have free group actions, then we can quotient out the space under the free group action. And down the line, that has the effect of simplifying or reducing the burden, computational burden in solving our underlying optimization problem. Of course, even if the symmetries are not really acting, one can have a geometric invariant theoretic approach, a la Mumford and others, and chop out the bad orbits and still power through. But so far we have stuck to a classical invariant theoretic approach. So we're sort of treating f, g as a tuple in the conjecture space, and we define this this set capital G, which are effectively general linear matrices over reals, and their purpose is that they can massage this inequality into many equivalent forms. So we found that that indeed forms a group, and not just that, every element of it can be uniquely written down in the form given by the matrix A, and we understand a lot of interesting group theoretical properties in this situation. So one of the central things we realize about this is the appearance of a subgroup, which is the dilation group. So you can easily imagine that if f is less than g, dilating this by some positive number doesn't change the inequality. Dilating this by a negative number changes the inequality. But in our formalism, we actually are agnostic to finding things that are, that can be, we don't care if we find things that are f less than, that represent f less than g, or f greater than g, because we are looking for conjectures. So it doesn't really matter to us what kind of dilations we consider, positive or negative. But for the purposes of the initial work, we considered positive dilations, and that gives a cone structure to this conjecture space, because we have also shown that this group acts freely on the space. The remaining group is H, and that corresponds to a different subgroup of G, which does not act freely. So nonetheless, if you look at the representation of a typical group element, it has three parameters, A, B, and C, and they are real numbers. And the only conditions are that A is not equal to 0 and B is greater than 0. So we can think of group elements as zeros of a function P of A comma B, which I've written down here as a function involving the delta function and the sigma function. And if you visualize the group elements in this A, B, C space, then group elements are exactly the zeros of this function. Now, in the months following this, we have found out quite a few more interesting things about this group, and we have refined our formalism. And in particular, we have realized that if we move to a setting where f is not less than g, but rather which is the difference of f and g, is either less than 0 or greater than 0, it brings out some other interesting structure. Can I lift this up? So if we sort of, I'm giving you an update on some things we're doing right now. So if we redefine our conjecture space to be functions that are continuous on some domain, on some compact object of Rn, such that H is either greater than the power of x or zero. That is to say that our conjecture is now represented by this function H, which never crosses 0. One rather puzzling thing we realize is that the space itself is not only a topological space, but it is also a group. And it's very trivial to show this. So in our refined formalism, the conjecture space is actually a group. And you can see why this is true. So this, if you consider this set and the operation of pointwise multiplication of functions, then you can imagine multiplying two conjectures, H1 and H2, where H1 and H2 do not themselves cross 0, then their product will also not cross 0. So they will also lie in the conjecture space, showing closure. The identity is the function that gives you 1 for every value of x, and inverse you can easily define as the multiplicative inverse. So you take 1 over h of x as the inverse, and since h of x never vanishes, it is well defined, and associativity is trivial. So in our refined formalism, the conjecture space itself is a group. So nonetheless, I'm going to speed up a little bit here. Yes.
But if they can then.
Well, we are always in tier two, and heuristically speaking, because we have F and G. That's an interesting question. One would have to work it out. Yeah. Yeah, so we actually have seen quite a few interesting features here. So in fact, if you look at the thanks for that question, nice question. So if you look at the typical group element A, capital A, you see the appearance of Hadamard matrices on both sides, there might be there are in fact representations which might be the Heisenberg group or some other affine group, but the key point here is that after doing this work, we realized that this is a very small group when compared to the actual full group of symmetries of this space, and that is because these parameters A, B, C are constants, so they're sort of trivial. They are trivially rearranging the inequality, and that's not super interesting per se. So we ended up figuring out another group action on the space, which figure that down. Let's call this G hat. And G hat will consist of functions which are continuous on R, 0, and they are bijective. So G inverse exists. So this is a much larger group that is indeed a function of your variables that you're working with. So it's no longer trivially manipulating the inequality, but rather it's applying a non-trivial operation to the inequality to give you another inequality, which is another point in the conjecture space. And the group operation here is composition. So if I gave you if you gave me a mathematical conjecture and a bijective function or a whole host of them that satisfy this criteria, they just can't vanish at 0. Then I can give you tons of other conjectures that will look quite different from the original conjecture. So potentially this is a way of generating more points on the conjecture space through this group action. So we are currently studying this group and trying to understand properties of this and how it acts on the conjecture space. But this is a much larger group than what we have considered so far. Yes. Yes, so we sort of discussed a bunch of things around the conjecture space and the group actions. So if you find a transitive group action, there is only one orbit, and that would be a crazy thing to conclude that there is only one inequality type conjecture. But it is possible. So for instance, we have considered finding equivalent formulations of known inequalities through the action of a group. We have discussed the possibilities of finding webs of conjectures. And you're asking an important question, because one reason a conjecture might be important is the impact it has on generating other conjectures, that they bring us closer to generating a vast amount of new mathematical result. And so we don't have a definitive way of doing this in a principled manner. Through this group action, we have one potential way of looking at some parts of this space. Does that answer your question? Yes. Okay. Okay.
So everything development has impact about the
Potentially. Very interesting question again. I mean, so how would you go about? All right. As in, why do you suspect that that might hint at the existence of complex numbers? Right. Yeah. Yeah. Yes. Yes. Ah, I see. I see now. Okay. Okay. Yeah. That makes sense. Yeah. Potentially. What we realize is if you remove the bilaterality condition, then this is no longer a group under composition. So it doesn't act on the conjecture space. So nonetheless, thanks for the ongoing discussion. Did you have a question? All right. So we worked out some interesting subgroups of this. We talked about the dilations group and quotienting out by the dilation group will give you some sort of a cone structure on this space. But right. So we have identified some other functions, some other subgroups of the space. And because the group is parameterized by these three parameters, and we have shown in our work that it is a Lie group, and that the conjecture space and the space of relations are Farad manifolds with some sup norm. So using those parameters A, B, and C, we sort of here's a visual representation of various subgroups of the group represented here, and what we can show is that these groups are matrix groups, and that they're potentially very useful in the machine learning pipeline that now follows. A quick note about two of the groups here. So it's J1 and J2. They turn out to be freely acting on the conjecture space, and they're also maximal in some sense. So here's our algorithm that generates conjectures. It effectively, the high-level approach is you sort of initialize in the space of relations, and you use some basic machinery that is known to physicists, mathematicians, computer scientists, called gradient descent, to approach the conjecture space. And every time you hit the conjecture space, you get a conjecture that is true on as much data as you have supplied in your compact set. And so in effect, in the language of computer science, this is a sampling problem. So as you can see, we sort of have a twofold approach. On one hand, we are trying to develop an understanding of the entire space itself. And on the other hand, we're sort of using computational machinery to sample points from this space. And the vision is that the more we understand about this space, the better will be the machinery that can find you interesting conjectures on this space. Now, before I state the algorithm in more detail, it might be worth asking, where are the good conjectures, right? In this conjecture space, which can be defined as the zero of some loss function. The loss function captures effectively how many counterexamples to your mathematical statement lie within your provided data. So, every conjecture, if you think of theorems of the inequality type, simple things like, e to the x is greater than 0, or, trivial things like 4 is greater than 2, and so on. They are all pointing to this space. But so is the prime number theorem, and so is the Riemann hypothesis. So surely, they all appear in this space, and this is true because of the nature of our construction. So yes. So we hope this. So one of our good friends, with whom we have a lot of conversations about this, is Yang Hui, and he pointed out that there are volumes and volumes of equivalent formulations of Riemann hypothesis. One of them is called Robin's criteria, and you can Robin's criteria is satisfied if and only if the Riemann hypothesis is true, and the criteria can be stated as an inequality involving the divisor function.
There is in particular on the net.
Yeah, thanks for that question. So because we are in a Banach manifold situation, we only have a sup norm to it, so we don't have a metric on this space. But if we specialize from the class of continuous functions only, then we can give more structure to the space. And what is special about a potential metric on the space is we will make it equivariant under the isometries that we are finding of this space. And the loss function is also going to be an invariant under those isometries.
But you don't know for it, like there could be like cycles.
Yes.
Could be at the center of the snowball from here to cycle.
Yes.
Which you don't have any cycle.
No, I mean, as long as we stay on the conjecture space, we are good. And with this, yeah. So the algorithm is trying to solve the sampling problem, and whatever geometry we impose on the space will help us generate more. And you might get things like cycles of conjectures. We have attempted to think about questions like when a conjecture, when a mathematical statement implies another thing. What does that actually mean in terms of the operation you might have to do on the first statement to go to the next? Is that something that's facilitated by a group action? Potentially, we don't know. We don't know. Yes. All right. So in our algorithm, there are two inputs, and I'll do a short demo, which will absolutely go wrong because a live demo always goes wrong. That's a theorem. So there are two inputs to our algorithm. One is some a box of functions in which you can throw in whatever you like. You can throw in a prime counting function, divisor function, or whatever kind of manner you are interested. And the other is this set omega, which is you pointing out on what kind of or on what subset of Rn you want to execute your computations, such that your machine starts learning. Right? And we will also take a few liberties. We'll put down the mathematician's hat and put on the physicist's hat and treat the prime counting function, for example, as a continuous function. So let's look at some results. So I think there might be one or two typos here, but other than that, I think 24 has a typo, inequality split. So when we first wrote down the most basic version of this algorithm, we realized two important things. One is that how easy it is to generate these conjectures. And the second is that we are rediscovering some old known conjectures that are still unresolved. So one of the first things that popped up was number 5, which to the knowledgeable number theorists here, unlike myself, is the subadditivity of the prime counting function. And turns out that was conjectured by Hardy and Littlewood exactly 100 years ago. And in the mathematics community, it is believed that that conjecture is actually false, but it remains unresolved. And the counterexample is expected to lie for a very large value of A and B. Since that looked quite terse, we bothered to Google and found that connection. It was previously not noticed. We sort of went bananas with this, and we started generating lots and lots of conjectures involving the prime counting function, and we had time to look at only one in detail. Broadly speaking, a lot of these conjectures are going to turn out to be false, and we have not done. We have ignored the safety advice from our diagram and generated, whatever we could. My apologies. Pi is the prime counting function. So it's the number of primes less than or equal to x. Right. So so we looked at the first conjecture, which is pi of A times B is greater than pi of A plus pi of B, and I showed this to my other who is treating Stanford at the moment, and we could show asymptotically this checks out, and then we quickly had to reach out to card-carrying number theorists or other knowledgeable people. So we sent this conjecture to Yang, and Yang said, "Oh, I can kind of prove a subcase of it, but I had to invoke Rosser's inequality." So what is Rosser's inequality? So with the help of Yang and Ilya in the London Institute, and with some conversations with Thomas Fink, we were able to prove that this is indeed true for all A, B greater than or equal to 17. For those of you wondering why can't we check the remaining cases, the case that we haven't been able to check is when A is less than 17 and B is not. That's the case that still remains open, but I suspect that is going to be true. So I'm sure the distinguished number theorists here can prove this over the lunch break. So another thing we realized is that we can generate conjectures involving many different variables and different degrees, and this can become a very interesting tool for folks working in the joint departments of mathematics or number theory. And the best application of this is in its current state is presumably a situation where you expect a good conjecture, but you don't know what its form might be. And if you can parameterize the space around it, you can use this technology to come pinpoint specific form. So this is the theorem. I won't bother going through the steps, but the most important result we needed to prove this was number 16. Is the function formula, and it bounds the common function. Two other functions. It's a rather simple application of known result. Questions? All right. So we sort of in the meantime we have made attempted to make conjectures in many different areas of mathematics, in many interesting problems. One of the things we looked at was finite simple groups. And finite simple groups are the primes of groups, and they play an important role in theoretical physics as well. And they are two generated. So a simple group is something that doesn't have a non-trivial normal subgroup, and they are always two generated. And there is a famous conjecture by Laszlo Babai from a few decades ago, which says that corresponding to a finite simple group, corresponding to a finite simple group, you can construct its Cayley graph and ask the following question: what is the diameter of the Cayley graph? So effectively, the diameter is the number of group elements you need to multiply to generate a generic element. That's the diameter. So Laszlo Babai conjectured that the diameter is upper bounded by the log of the order of the group raised to the power c. Now, I'm going to understand that people expect c to be exactly equal to 2, but it is a universal constant. It's not known what the actual is. So we wanted to do something similar. So we generated some amount of data using groups, using this package called Groups, Algorithms, and Programming, GAP for short. And we could generate conjectures about the diameter of a finite simple group. Diameter of the Cayley graph of a finite simple group in terms of the order and traces of its generators in some permutation representation. And I was tempted to remove the conjecture number 4, but I kept it there because although it looks ugly, it sort of highlights why the domain expert is important here. And this is potentially a completely useless conjecture. Number 4, I do not know, but it goes on to show that when you talk with domain experts specializing in fields of analytics, they can pinpoint you to areas where you expect a good conjecture, and those conjectures, they might check all the criteria that Robert Diagram laid out. So this is not a beautiful looking conjecture, number 4. But yet, it makes our slides. I think I've already mentioned this point that when we're within this formalism, at least computationally, we can consider the situation f is equal to g when f is neither greater than g or less than g. So we have played with generating some conjectures which are mathematical inequalities through this formalism as well. So I'm going to quickly wrap up unless there are some questions at the moment.
It's not greater than how do you find it?
So it's not in the. If they're like this, then they won't satisfy both criteria because they'll overlap. So this has to be true for all x. If f is dominating g, or g is dominating f, but if neither of them, but if neither dominates the other for any value of x, then the only logical conclusion is f is equal to. So if I were to be more precise, I would write this. Yeah,
it's not the converse, it's not the not of this.
Yeah. Right. So what do we do with this technology? We have sort of touched upon most of the points here, but first of all, it seems that at least in the class of conjectures we have considered, we are able to assign a well-defined mathematical space. And after further specialization, we can assign mathematics to the space because we have some norms. There are interesting connections to logical representations, and one can study simpler things like Boolean functions, as test cases of this. I've mentioned briefly what the connection to O minimality might be, but it is facilitated through definable sets. So one is always tempted to consider other representations. So far what we have done is completely symbolic AI. We have ignored things like GPT or language representations, or even representations that automated theorem provers are used to, higher order logic. But moving forward, since language representations, although they may not admit such special logic structures, they are indeed very good at semantic reasoning. And the way I see this venture progressing using those representations is that language representations provide a high-level idea of where you might want to go, and coupled with a symbolic approach that we're talking about here, you can actually pinpoint to a specific mathematical inequality. We've been chatting with some folks interested in automated improving, and right now we seem to be able to generate conjectures. We don't know if we're generating good conjectures. We're generating some good conjectures, but we want to be more deliberate. We have issues of what is an interesting conjecture, and qualify them and bake them into the algorithms. And down the line, one can consider looking at having a quantum backend, a la Shubhayan, who is an expert in quantum theory, and familiar with those applications on that front. So far, what we have done has not involved incredibly interesting machine architectures. We have solved a very simple optimization problem, but it is important that when we scale up, when we consider the knowledge base of mathematical inequalities into our framework, our optimization problem is going to get harder and harder. And in scaling up our framework, would need to consider more interesting machine architecture, and there's very many of them. There's a lot of work on invariant networks and graphs. Another way to sample functions is through Bayesian means, which is through Gaussian processes. Right. So outside of mathematical applications, we have considered other things, the things that have been difficult computationally as well as theoretically, things like finding the ground state energy of the physical system, and we have made no progress on that. But I might show you something about this in the demo. But keep your expectations. Thanks to some of the interesting questions we have already touched upon. Point number 7, that what is the role of conjecture that might be implied by one conjecture might be implied by the other, and there might be webs of conjectures that can be studied through this. One interesting idea that Subhan and I discussed quite closely is wanting to rethink undergraduate classroom teaching in mathematics in light of things like ChatGPT. So typically we only consider the manner of assessment for students in a classroom setting is the questions that the answers are known, and we want to consider different form of assessment where the answer is not known, and the student is forced to think outside of the box and forced to settle the conjecture. And this only works if you're able to quantify the hardness of a conjecture. If you can quantify the importance of a conjecture, that would be a good practice. There are various limitations. They're mostly limitations, actually, in the course of the entire pipeline that I envision. But we need, right now, we need functions that can be easily computed, and we can easily generate very complicated looking conjectures, and they will look quite ugly, but will still be true. And what do you do with those things? As I mentioned, the curse of dimensionality is something that we have to consider down the line. So this is the paper that we put forward a few months ago. Feel free to have a look at this or reach out to us. These are my friends with whom I have done this work. I mentioned Shubhayan already. He's an expert in quantum theory and he's housed at the department. Rahul is a friend from high school, and he is an expert in analysis, and he's sort of gone to Berkeley now to work on quantum computing. Do not play chess with these guys. You have been warned, as I found out earlier this year. Right. This is sort of the first talk I gave on this was at Oberwolfach a few months ago, and they created a very nice cartoon summary of this talk. Sort of highlights the role of symmetries in this endeavor, and sort of summarizes the framework quite nicely. I should mention that currently I'm at the computer science department, and I'm sort of working under the accelerated program. So where we are a bunch of scientists or mathematicians who have embraced machine learning, and we mostly make bad jokes and end up appreciating them over very many Zoom calls and meetings. This is probably for our time. All right, let's make some conjectures. So we have around 15 minutes or so left. I'm sorry for the very long talk. Are there any questions before I can? Fine. Talking about it, but those are things that we consider because we're mostly in this domain where we can compute things and we assume that we can resolve the conjectures that we come up with. Yes. Yeah. So in my limited interactions with the communities of Isabel and Lean, I realized that you can encode a mathematical statement. I played around a little bit with Isabel. So upon encoding, by the way, the syntax is not nice, but there's a way out. You can ask ChatGPT to generate Isabel code. So encode the prime counting function. It will be a nice piece of code. The manner in which it works is you encode the mathematical statement, and it will give you sub-goals that you need to achieve to completely prove that statement. And in some cases, it might be able, in some trivial cases, it might be able to execute the inference itself, but it's more of a proof verifier in the sense it is being used right now. But there is increasing amount of work now in light of machine learning in starting to complete some of these steps in between. And there are also other approaches. So folks in my department, such as Mathea, Yannick, they have a more sort of mathematician-centric approach to proving statements. You might think that, okay, this is how the proof might go. These are the proof techniques that might be at play, and ultimately into a proof. But what exists now is a huge corpus of mathematical proofs of statements spanning many different areas of mathematics. There's ongoing work now, from colleagues on utilizing language representations to solve this incredibly hard search problem of finding the proofs. So as far as this talk is concerned, we are mostly generating conjectures, and we are not attempting to prove things. But down the line, interaction with proof systems will become more pronounced.
Yeah. So the elaborate question is that you talk about the space on the metric of space of indexes.
Yes.
And that naturally derived from the space, the metric of space of continuous function. Is that right?
So what we have shown is the space of conjectures is a Banach manifold, and it lies inside the space of relations. It's also another Banach manifold. So we have a norm, but we do not have a metric. So in order to assign a metric, you need to give more structure to this space. You need to,
Suppose your function doesn't need a very specific set of functions, say model function.
Yes.
More or less, and then natural metric from the space.
Yes.
Will be able to consider.
Yes. Absolutely, and there will be this interplay of equivariances on both sides that you can easily take care of.
There's a sense in which you can say some theorems are closer.
Yes, absolutely. So we can already say two of our given conjectures, what is the distance between them, because we know the norm. Because soup norm is well defined here.
Well, but yeah. No, I got an input, and then try to see I can derive a natural metric of the space conventions.
It will induce some sort of a method.
And for example, I want to understand statement. Let's take an example, right? Let's compute the birth certificate simple one.
Sorry?
Birth certificate.
Okay.
Let's take two conjectures. Conjecture A and
Okay.
conjecture A implies conjecture B.
Yes.
But the disproof of conjecture A does not disprove conjecture B.
Sure.
Or otherwise, proof of conjecture B does not imply conjecture A.
Sure.
How do you explain with these kind of statements?
Yeah, so right, fantastic question again. We don't have a clear answer yet. I mean, what we know is, there might be a logical operation of implication which might relate to certain kinds of functions, and that might shed some light into baking in things into a formalism that relate to mathematical statements. A implies B. How does that appear? How do we formalize that in this framework? These are good questions that we hope to visit. All right, in the very short amount of time we have, let's generate some conjectures. So as promised, there are only two inputs. One is a box of functions. So here, as a starting example, I've created the divisor function. Yes. Oh yes, sorry. All right. So so here I'm considering two functions. Let me see how I define this. Oh yeah, all right. So div0 is the sum of the divisors of an integer, and prime pi of x is the prime counting function. Just throw in the Louisville lambda function, which basically finds out whether the number of prime factors of a given integer is plus or minus 1, is odd or even. And let's generate some easy conjectures on this. Sorry? Probably that's the right notation. So this is a trivial conjecture, more trivial. All right, let's have a look. So this is a conjecture that should obviously be true. What I'm plotting here is effectively the difference of f and g as a function of your one variable. Yeah. Does anyone have any interesting things they would like to try out? Switch this off. Let's have the log integral. Let's just have the log integral and the prime counting function. Let's see if it can rediscover the prime number theorem. Kind of. It's off by a factor of 2. So what it's saying is twice the log integral of x dominates the prime counting function, or is dominated by the prime counting. There's another one. Okay, this one is trivial. Let's go to higher dimensions. All right. Okay, this looks interesting. So for this integral, so this is the log integral of x plus 1 try for that minus phi of x times y minus twice of phi of x plus y. Again, just to emphasize, this is a conjecture. This may not turn out to be true. And just want to have a guess how many some queries to the log integral function and the prime function. So one of the reasons we chose to work with some number theoretic functions is, there are interesting statements that are made that there are no accidents in mathematics, and even more so in the case of number theory. So we required 10 calls to the function of log integral and the prime common function. It's quite interesting. So using these tens of evaluation we can generate some conjectures. Let's generate even more complicated ones. Let's up the degree. This. It is beginning to sweat a little bit. What's this? So the plots sort of show how the conjecture or the difference of f and g, that is h in our formalism, actually dominates the zero, right? So it seems to be true on the data. And this conjecture is saying that 3 times the square of the log integral x times y and other combinations of log integral and the prime counting function and the sum. So this, one point I'm trying to make here is that the ease with which we can generate these conjectures actually highlights the importance of talking to the domain expert here. So this is perfect to be utilized in a situation where you expect a conjecture, but its form is not known. Or if you can address some of the interesting questions that came up about the implications of one conjecture about the other, or questions around the group structure on this space, they'll allow you to generate more and more interesting conjectures. So in short, this is an example of an organizational principle for mathematical theorems or conjectures of a when coupled with some of the other interesting approaches to machine learning for mathematics, we have seen, we talked about Yang and others, this can be a very interesting tool for the modern mathematician or mathematician embracing machine learning and Bitcoin to accelerate their own discoveries. Yeah. We can keep joining conjectures, or we can wrap up. So it 10 times. Yeah. Well, we're not invoking that. Actually, training set size is 10, and it's much easier to visually see why it's true by plotting it rather than evidence. Third one can also make evidence for this on some 10 points. You can say that, okay, I'm going to increase the test size to let's say 1,000, and let's collect evidence in favor of that. It checks out. No counterexamples so far. So the range in which it is searching for counterexamples is for numbers up to a million. Oh, of course, feel free. Equalities. Yeah, so one of the things we have considered playing with is the Arthur-Strauss conjecture, which appears in the form of an inequality. One can also look at the Pollard's conjecture and look for similar examples. So it's possible to do this. Yes, and I would be so afraid of coding in coding live that I would do it as my homework. Is it going to be true that the more you add, for the I mean, the code for this Yes, absolutely. So that's a brilliant question. So, one of the properties that we realized is the sharpness of the information. So we are in the domain of inequality, but if we of course want to generate sharp inequality such that if we take them a little bit, then we have disturbed the whole thing and no longer work. So for example, we talked about Robbins criteria. One hypothesis. If you tweak that a little bit, it completely destroys the inequality. But that is not true for trivial conjectures. And these things can actually, I think that's what I believe, that such a such strictness can be quantified through some local properties of the conjecture space. So if you're if you're on the conjecture space and you're sitting on the prime number theorem, locally the surroundings will look a little different geometrically than when you're sitting at another point where let's say x is less than x squared. And those are some of the things we're trying to quantify. Right? So we have some empirical results on that front that show that maybe the way to quantify the importance is perhaps through geometry. But again, this applies only to this class of conjectures that we're looking at, which are inequalities. It's possible that there are other ways of going about. Yeah, greater than 0.
For example, you mentioned the matrix structure, you can but then presumably you can only care about the norm distribution. But then they also do something you or other. Presumably we have a metaphor which has more of the structure. Homology or not quantity, but structure. So is it a sensible question to ask for the topological geometry complexity of manifold that may not depend on the total number of the operators of the.
It's entirely possible. I can't immediately answer that, but yeah. So as we're discussing over Suresh's question and follow up that whatever it is that whatever the class of conjectures you're looking at or kind of functions that appear, there if something is known about the structure, then that will induce some structure on the conjecture space itself, and then you're well placed to exploit that.
Thank you. One would say that conjecture is unique conjecture. That's not heard from.
Yeah, it's not first at all, and yeah, that's a very interesting question. I mean, maybe one can write it down as an inequality. So in which case it will be a point on the conjecture space. Yeah. So it would be a point in our conjecture space. Yeah, and so will be all sorts of important and unimportant results in mathematics. They will in the form of inequalities. There will be points on the space. And the interesting bit is if you know their functional forms, then you can already start. You can pinpoint where exactly they are in the conjecture space. You can look for conjectures around that space, or you can emphasize that conjecture and attempt to find other interesting conjectures around it.